Okay, the next section we're going to do today is infinite limits. And the first thing I want to do is kind of explore a function to go over infinite limits. All right. So the function I want you to kind of take a look at is let's explore the limit as x goes to 0 of 1 over x squared. Okay? So, when I look at this limit, I can't plug in 0, right? Not going to work. So I can't figure it out that way right now. And there's no factoring you can do. There's no complex fraction you can, there's really no manipulation you can do to this. So what we need to do is think about this one. I want you to think about what happens, because it's clearly not defined at 0, right? But is there a hole at 0? Remember, for there to be a hole, whatever was causing the issue in the denominator has to cancel. That's not canceling, is it? Not a hole at 0. So what we're going to do is think about, well, what's really happening with this function as we get close to 0? So how do we get close to 0? Well, if we're not going to graph it yet, what can we try? Just plug in some numbers, right? Let's try plugging in some numbers as we get to 0. So maybe we'll start large. Well, if x were 2, what do I get? Remember, f of x equals 1 over x squared. So what happens when x is 2? I get what? 1. Okay, I'm going to get closer to 0. What happens when x is 1? Okay, I'm going to get closer to 0. So what happens when x is a half? Come on, guys. You have calculators. You can't do it in your head. Well, first of all, what's 1/2 squared? 1/4. What's 1 over 1/4? 4. All right, let's get even smaller. What's smaller than a half? 1/3. What's 1 over 1/3 squared? Let's jump up and get really close. So let's go to a 1/10. What's 1 over 1/10 squared? 100. In fact, the smaller and smaller I get, what's going to happen to this set of numbers? It's going to get bigger and bigger and bigger. Does everybody see that? That's great for the right-handed limit, right? In fact, as you get 1 over, I don't know, 100 is what? 1, 2, 3, 4, 10 is 10,000. You can see real quick, 1 over 1,000,000 is going to be a really big number, okay? As it approaches 0, it doesn't have a value at 0, but as it approaches 0, it gets really big. In fact, it's going to keep getting bigger and bigger and bigger and bigger, and it's going to go to what? Infinity. So now we know that when we approach x from the right, be careful, remember with limits, the right and left matters. That is infinity. Question is it infinity on the other side? Well, I'd have to do does anything change? I'm squaring it, so isn't it all going to be the same? Right? So as I approach from the left, it's still going to be 1/4, 1, 4, 9. It's still going to positive infinity. So what can I include the limit as x goes to 0 of 1 over x squared equals? Infinity. Infinity. Okay. I want to adjust this a little bit. I want to do the same thing, but now I want to do it without 1 over x squared. Okay? I want to do it without 1 over x squared. And you know this. If you were to graph it real quick, we went over common graphs. This was one of the common graphs we actually put up real quick. If you remember, the graph of this looks like... Look, do you see what's happening as it approaches 0? It's just going up on both sides. All right? How does this change if I make it 1 over x? I'm not going to do the charts again. You'll get the idea. How does it change if I make it 1 over x? The limit as x goes to 0 of 1 over x. So, okay, when I approach it, well, I'll do the charts again. That's fine. I got to look at it from the right-hand side first. That means I'm plugging in positive numbers. Same idea. Two. 1/3 is what? Yeah, it's still going to go, it's just not going to go as fast, but isn't it still going to go to infinity, everybody? Yeah, what's 1/10? 10. What's 100? What's 1,000,000? A million. As you get closer to 0, that is still going to approach infinity. So yes, that's infinity. Okay? What about from the left, though? If I approach it from the left, okay, now I'm plugging in those negative numbers. I don't have that square to make everything positive. Okay, so let's do it. -1 is, -1/2 is, -2, -1/3 is, okay, where's it going to? Yeah, -1 million is 1 over -1 million, which is -1 million. All right? It's still going, but this time it's going down. So this time it's going to negative infinity. What does the graph look like? We did this graph. It's this, but then it's down, right? As x approaches 0. Now, when the left-hand side equals the right-hand side, even if it's infinity, we can say the limit goes to infinity. But when the left-hand side does not equal, does infinity equal negative infinity? Absolutely not. When the left-hand side does not equal the right-hand side in the limit, what do we say the limit does not exist? We'll start using DNE. This is infinite limits. These are not holes in your graph. What are these things called? What's happening on both of these graphs? It's happening on both of the graphs, whether the limit exists or not. It's an asymptote. Remember that? So if your denominator doesn't cancel but causes issues, you likely have an asymptote. How do you know for sure? As long as your limit is going to infinity or negative infinity, doesn't matter. It could be different on both sides. It is a vertical asymptote. We'll get to horizontal asymptotes next week. These are vertical asymptotes in your graph. Another little thing I want to point out. Is infinity a number? Is infinity a number? No, because I used to say that last semester, I think. But it's not. Infinity is not a number. Technically, and you'll see this written, technically, none of these limits exist because infinity is not a number. Does that make sense? But because if they're both going to positive or they're both going to negative infinity, it gives us more information to say infinity or negative infinity versus does not exist. we use the symbols. All right, but you'll see it written at different things in your notes. Technically, it still doesn't exist, but we don't put DNE because it still gives us information about the graph. We do put DNE when they don't match up, okay? So these are infinite limits. This is different from what, and I like to teach these lessons on 2 separate days because, and it usually just works out that way in the schedule. What we're going to do Tuesday's class is talk about limits at infinity. In other words, what happens when you take the x value to infinity? Does that make sense? That's different from an answer being, you can take the x value to infinity and still have the limit at, of infinity. All right, but today we're going to focus on these infinite limits. So there's not much to it. I'm going to give you that formal definition though. Okay. So here we go. That's pretty much the whole lesson. It's crazy. But we'll do some examples and I'll give you that formal definition. So infinite limits. Let's take a look. So guess how we're going to start. Suppose f is defined for all x near a. If f of x, okay, so that's your y values, that's your outputs. If f of x grows arbitrarily large for all x, arbitrarily, that is the word. Again, it's all written out. If you don't like my writing. Arbitrarily large for all x, sufficiently close but not equal to a, then we write the limit as x goes to a of f of x equals infinity. I am not going to write the whole thing out, but obviously there is the flip side of that, right? If f of x is negative, so they use the word magnitude. They say if f of x is negative and grows arbitrarily large in magnitude. So what's the difference? What does magnitude mean? Distance away. That means it's going negative. Or what you might say is arbitrarily smaller and smaller and smaller. I'm just going to do this. Then the limit as x approaches a of f of x equals negative infinity. You get the idea. I'm not going to make you read. You can read it on the notes. You know, in both cases, technically, the limit does not exist. Remember that. All right? In both cases, technically, it doesn't exist. So there's not much to the definition. You've seen it above. Adding to that, add this part to it. If the limit as x goes to a from the right of f of x equals infinity, and the limit as x goes to a from the left, or vice versa. You know what I mean by that, right? One could be negative, the other could be positive. Then the limit as x goes to a of f of x does not exist. That's when we write does not exist, when they go differently, that's all. The other thing I want to recap is the vertical asymptote, and then we'll go through an example where there's a vertical, a hole, and you can see the difference, okay? The other thing is the vertical asymptote. And here we just say if the limit as x goes to a of f of x equals either positive or negative infinity, the limit as x goes to a from the left equals positive or negative infinity, or the limit of x goes to a from the right. If any of those occur, okay, any of them, even if it's just coming from one side and not from the other side, that's what this is saying. So the first one says, hey, they're both going to either positive or negative infinity, or the left is going to positive and negative infinity, or the right's going to positive and negative. If any of those things occur, then the line x equals a is a vertical asymptote. Even if the limit doesn't exist, if one of those things occur. And the other thing you can jot down for yourself if you want, just remember, if the factor in the denominator cancels with a factor in the numerator, you have a hole. If it does not, then it's a vertical asymptote, okay? So if a factor in the denominator cancels with a factor in the numerator, then you have an open hole, which is called removable. We'll get to this next week. It's called a removable hole. It's almost like everything's perfect in the function, but I popped something out of it. It's removable hole exists. If that's the case, you have a removable hole. Here's my question to you. Does the limit exist? If you have a function with a removable hole, does the limit exist? Yes. So don't forget that. It's all written in the notes. If the factor in the denominator cancels with the factor in the numerator, you have an open, removable hole, limit exists. Okay? If it doesn't cancel, you have a vertical asymptote which is not removable. And the limit is positive or negative infinity, or the limit does not exist. Okay? So again, I'm just highlighting some of the notes that are in here. If you go through and read that, you're like, oh yeah, that's what she said in class. So let's do an example. One example. Here it is. So I'm going to give you a function, a nice easy one, not going to be a crazy one or anything like that. So here's the function. F of x equals x squared minus 4x plus 3 over x squared minus 1. And we are going to find a bunch of limits. So here's the limits I want to find. First limit, I want to do as x goes to 0 of f of x. Then I want to do the limit as x goes to 1. And then I want to do the limit as x goes to -1 from the left. And I want to do the limit from the right. Okay? So we're going to find these limits, and then we're going to talk about those. So for the first one, so for A, well, that's just, okay, that's the limit. Just ask to find that limit. Remember, what's the first thing I said to you? You could always just try doing is what? Plug it in. Okay, I don't care about anything else. I just want to know, hey, what's happening at 0? What's the limit at 0? What's the function doing at 0? Right before and right after 0. Always try just plug it in. Can I plug in 0? And will I get an answer? Yeah, I can plug in 0, right? 0 minus 0 plus 2, right? I can do this in my head. 0 minus 0 plus 2. 0 minus 1. What's the answer? So there are limit problems that are just that easy. Don't just assume you have to go through all this craziness. Sometimes it's as easy as just plugging in a number. Okay. Can I plug in 1? See, if I'm asked to find the limit as x approaches 0, I can plug it in and I'm done. It's -2. That's it. Right? 0 minus 0 plus 2. 0 minus 1. Oh, it was 3. Yeah. All right, I made it. How many classes without doing that? I made it 3 whole classes. That's pretty impressive. I will often take a number and write the wrong number in the next line, so you got to catch me on that. All right? That's a 3. You're going to be like, where did the 2 come from? No, it's clearly not a 2. It is a 3. So let's make that a 3. Which makes the answer -3, right? Okay, good. All right. What did I do? Right? Isn't it 3 over -1? 3 over -1, right? Oh, no, it's okay. Okay, but to do the next one, we have an issue. You can see right away, you can't just plug in 1 to that problem. So to do that, let's come up here and let's manipulate this a little bit before we even put a limit sign in front of it. In other words, let's see what this looks like. What? Factored. What's x squared minus 4x plus 3 factored? Yep, -3 times -1 is +3. And then if you add -3, -1, you get -4. Good. Yeah, if you can't Factor trinomials. Practice that before you move on with the class. Factoring a trinomial, okay? That's something you want to do. I know they teach you the AC method. It's like a long method. if you know you're taking a lot of math courses and a lot of calc courses and you're going to continue with math, yeah, try to get the kind of guess and check down pretty quick. All right, and just figuring rainbow. They used to call it the rainbow. Did you have a teacher call it the rainbow method? The little rainbows. I don't know. Anyway. All right. What's x squared minus 1 factored? Go for it. Yep. Okay, so before we finish this problem, based on everything you just learned in literally the last 15 minutes, do we have a hole somewhere? Where's the hole at? X equaling what? Which one's the hole? Based on what you just learned, everything I wrote out, where's the hole? Yes, because aren't these going to cancel? That means I have a hole at the x value that causes this to go to 0. I got a hole at 1. Do I have an asymptote? Asymptotes occur when the factor doesn't cancel. Do I have an asymptote anywhere? At -1. I'm going to have an asymptote at -1. How do I know that? That x plus 1 in the numerator, in the right denominator, isn't canceling with anything. I can't plug in a -1 to that problem, right? Because that's going to be an issue at -1, we are going to end up with an asymptote. So these are the things you can kind of look at before you even do the limits. Like even regardless of where you're asked to take the limit to 1 or -1, you can look at that problem and go, oh, got a hole at 1, got an asymptote at -1. So completing this one, putting it in factored form and canceling it, can I cancel these then? I can take the limit yes. See how this factor cancels? Whatever would cause this factor here to be a 0 is a hole because it cancels. Okay? And we see it here. It cancels away. What this will tell us is what would be in place of that hole if it wasn't there. Okay, the limit exists. Remember, if you have a hole, your limit still exists. All right? Because from the left and the right, they're both going to approach that hole. And where is that at? Well, at 1, when I go and plug that in, yeah, that's a 3. It looks like a 2. There you go. When I plug in 1 here, what do I get? I get -2. Do I get -1? Do I get -1? Do the math. Don't trust me with basic arithmetic. Like, if it's the most basic numbers, definitely don't trust me. -2. I get -2. No. Yes. Everybody agree? Everyone agree? So what does that mean in terms of our graph for part B? That means somewhere when the graph hits 1, right? Somewhere when that graph hits 1, it's getting here, there's a hole, and it's continuing. Okay, there's a hole down here at -2. All right, there's a hole down there at -2. Is it -1? I asked you guys like 5 times. Yeah, it's negative. I thought so, and I'm going 2. Okay, no, it's -1. Gotta speak up. -1. So yeah, -1, 1. We have a hole. That's the next part. Okay. All right. So that's your hole. How do I know? Why am I taking -1 from the left and right? I know there's an asymptote there because this piece doesn't cancel. Do you see this x plus 1? It doesn't cancel with anything. what would cause x plus 1 to be 0 when x is -1? That's going to be an asymptote. So that's something you want to get in your head. And then you want to bring it back after I hit you with derivatives for a whole chapter. When we start graphing in chapter 4, you're going to come back to this. Okay? All right, so let's take a look at our asymptote, because we know we've got this asymptote. What you don't know about the asymptote, we know it's an asymptote because it didn't cancel. We don't know if they're both going to positive infinity, both going to negative infinity. We don't know any of that. All right, so we got to figure out how we get that information. Okay. So I have this function. The x minus 1s went away. We can get rid of those. We don't care about those. We're just looking at x minus 3 over x plus 1, right? So here's the thing. You know now there's a vertical asymptote at -1. What you don't know, it's what's happening when you approach from either side, right? Is my graph going up? So we're going to approach from the left first. So we're going to approach -1. So this is what we know so far. We know at -1, I got this going on. What I don't know is when I approach from the left, is my graph shooting up or is it shooting down? How do you think you're going to figure that out? Without graphing it. You might have said it. I'm not sure, Leah. Yeah, you just plug it in. And you don't even have to plug in a number. You just got to know, like, if it's negative or positive. Right? So we're moving up in math. We don't have to sit there and plug in exact numbers. I want to know, all right, what's a number that's pretty close to, and you got to get pretty close, right? That's close to -1, but smaller than -1. So visualize it. You don't even have to come up with an exact number. You know what I'm talking about. I want a number that's kind of close to -1, but not at -1. If I take that number and I subtract 3 to it, am I going to get a negative or a positive? Negative, right? All right, so let me do this. Let me do this to make it a little bit easier. So let me get rid of, make some space here. So remember, I'm doing the limit as x minus 3 over x plus 1. And I'm going from the left. So that means I'm plugging in, I don't know, -1.0005. Doesn't matter what it is. When you subtract 3, aren't you still going to get a negative value? Now, if I put in -1 point anything, and I add 1, what kind of a number am I going to get? Negative or positive? Positive. No. Try -1.5. -1.5 plus 1 is what? It's negative. Isn't it negative? The larger magnitude wins out. Any number you plug in is going to have a larger magnitude than 1. Because you're going to plug in -1.9, -1.001. You're going to get another negative. So what's a negative divided by a negative, everybody? So that goes to positive infinity. Now, if you don't like that, go ahead and try -1.001. Plug it into your problem, get a calculation. You're going to get a negative number. That's how you know that one, negative over negative, is going to positive infinity, because it's going to be positive. Try it from the other direction. Look how it changes when we go from the other direction. So what you're doing here is you want to think critically, think smart, without having to do a lot of calculations. All right? So remember what we're doing now. Now we're going to approach 1 from the right. So now we're talking a number like what? -0.9, right? You're picturing a number like negative 0.9. If you take a number, any negative number, doesn't matter, and you subtract 3, aren't you still going to get a negative number, everybody? But if you take a number like negative 0.9, negative 0.8, negative 0.99999, and you add a positive 1 to it, what kind of number are you going to get? Positive. What's a negative divided by a positive, everybody? It's got to be a negative. So that goes to negative infinity. This is, think critically, instead of getting your calculator and just plugging in a bunch of really close numbers. All right? That one's going to go to negative infinity. That one's going to go positive infinity. I mean, don't worry. You will practice this on the next lab. Not on this lab, but you will be practicing this on the next lab. Because when it comes to those vertical asymptotes, the only way to know if it's going to negative infinity or positive infinity is to imagine putting a number really close to that vertical asymptote into it. Well, from the left, it's positive. From the right, if I were to ask you, I don't have it on here, but if I were to ask you, we'll add an E. How's that? We'll add an E. If I wanted the limit as x approaches negative 1, what's the answer? Yeah, DNA, because it's negative 1. All right, so we're not doing it in this unit, but chapter 4, you're going to start taking this information and you're going to start to graph it. So right now you're like, oh, I can actually have a really good idea about what's happening here. I know there's an asymptote. All right, I know that coming from the left, it's going up. I know coming from the right, it's going down, but it also crosses here and causes a hole. So it's kind of like, boop, boop. What I don't know yet, which information I'll get next Tuesday's class, because you're going to be so excited, right? You're not going to wait. Can't wait. Is horizontal asymptotes. Are there any horizontal asymptotes occurring in this problem? We don't know that yet. But we got a lot of information about our graph at this point. So that is a non-turning questions. Stop.